Okay. Hey guys, so I'm pretty much just going to be giving a sh not a short intro. I'm going to give a very extensive intro to the foundations of signal processing. Um, it has a really rich history, so I'm gonna pretty much take you through everything important that's ever happened in math. Um, but first, what a really important question to ask is, what is a signal? So a signal is pretty much any method of conveying information. And this can vary in a bunch of different parameters. So you have time, space, are two really common ones. But there's a bunch of different parameters that they can vary over as well. So some really common examples are sound, images, or voltages. Another really abused signal even is the stock market. So you can see here some lady listening to something. That's ECG, so how you monitor your heart health when you're in the hospital. And that's Mateos losing all his money in the stock market. Um, so hopefully that gives you a better idea of exactly what a signal is. Um, Usually in the context of signal processing, we're going to talk about it through time. That's what I care about more than anything. So it's going to be mostly based around that. Um, so I want to talk about one of the first signal processing tools, analog tools that ever existed, the sundial. So pretty much you have this tool that can kind of tell you the time of the day. Um, and you can see all it does is take the sun's position, the light from the sun, and it outputs the shadow. And you have like this little rock that you can kind of read as well. So all it is there's a notion of an input, some way that it's processing. In this case, it's analog, and it's pretty much just physics. And there's an output, so the shadow. So this is really important because it gave us the ability to do some kind of processing on measurable quantities. So uh, the light is measurable. You process it with the block, and then the shadow is pretty much the output of that. And this serves as a precedent for later systems. So things got really spicy with the birth of calculus. Um, Before this even happened, there was Euclid and all those people that worked on geometry and studying numbers. But the birth of calculus is when things really started getting important. You have two really important figures, Isaac Newton and Leibniz. So both of them are attributed with having started calculus. Calculus, if for those that don't know, is pretty much a study of measures, um, especially over a continuous space or an approximately a continuous space. You have it's not possible to fully quantify it based on measure theory, but you can get very dense representations of it, and so that's what we kind of take advantage of. Um, so the core concepts that we all know is the concept of the derivative, so the rate of change, how it changes over time, um, and the integral. So the integral is the accumulant, the derivative is the instantaneous rate of change. And you can see the two formulas there. So then the fundamental theorem of calculus just formalized this inverse relationship between the two. Um, and so you can see the explicit formula for the derivative at the top. You pretty much get an instant. You set this window over which there's a difference, and you try to make that infinitely small, measurably small. Um, and that's how that works. And then there's as well as the accumulate function. So all that does is sum up the individual uh, functions at the different instances with respect to that small infinitesimally small um, uh, pretty much area is what it is. Um, so actually I wanted to draw, but I don't think I can. Um, I was gonna show the Riemann approximation, which is honestly a pretty cool process, and you guys should look into that if you are interested. But the Riemann formulation of this gives some real insight into why or actually how integrals actually work, as opposed to um relying on this idea that the integrals are the reverse of derivatives. Um, so you can pretty much express the integral as a sum using the sum operator, which we do understand because it's discrete. Um, but anyway, so this is really important still because numerical measurement was not really, there was a notion of it. So you can, if I'm here, you can see that I'm small. If I get closer to you, you're going to see I'm bigger. But it was really difficult to measure things analytically at the time. So this kind of this kind of created a really powerful set of tools for measurement. That's the takeaway from that. And so you can essentially model how things change. And that's the really important part there. So on the left uh, is Isaac Newton, and on the right is units. Um, and I took these pictures from Wikipedia. So next is the advent of analytical tools. Oh, actually, also I didn't mention, but this all happened in the 1600s. So pretty much that's when math and science started getting spicy. Um, but the advent of analytical tools. So this is when people started realizing that calculus is really usable and can generate actually really important results. So there's a few key figures. You can see here Madhava of Sangamagrama. Maybe maybe somebody can correct me, but Jacob Bernoulli, Brooke Taylor, and Leonhard Euler. So those are these three. Um, and so I'm pretty much going to give you the canonical importance of their contributions. So you can see that Madhava Sangarama, this guy's some guy, some Indian man that was working on math, and I think they had a really cool like Indian school back then for mathematics. Um, and I don't know if this is an actual person or just like an identity of a collection of people. I didn't look too deeply into it. Just made this at 2 a.m. yesterday, but um, pretty much what ended up happening is that they used a, a lot of really complex geometric estimations of um or they developed a really complex set of geometric estimations of the series for these trigonometric functions. So they did this without calculus, by the way. So they just fully estimated this using geometry, which is pretty bizarre. Um, they did it for cosine and sine. Then more formally later on with the development of calculus, they were able to verify a lot of these results. And that's when Jacob Bernoulli first defined the limit definition of E. So you can see in the second one, that's the formal definition of E. So typically you would think that that might approach zero, but the truth is that it just approaches a constant, which is a really interesting property of it. And there's some proof that can be done to pretty much derive equation four. I've shown that in my other workshops before, but yeah,
When did approach one? It's like n goes to infinity, like definition two.
for definite. Yeah, so it seems. Oh, sorry, I said one. I should have said one. I think I said zero, right? Yeah, it would seem like it would approach one, but what it ends up approaching is just some constant. And you can approximate it very easily. I showed that in my workshop too. Um, I don't know. I actually don't know what precision most people use, but you can get really high precision and with only like 10 iterations, which is pretty surprising. Um, but anyway, yeah, the surprising result is that we thought it would be one and it wasn't. Um, so Yeah, so Jacob Bernoulli worked on that, and that's the silly guy in the middle. Um, and then finally, Brooke Taylor. Brooke Taylor is famous for Taylor series. So if you took Calc 2, probably suffered through that and you have an idea of what it is. But the really important takeaway from what a Taylor series is you can have some kind of function, and as long as it's uh continuous, and I think the continuous aspect of it is just locally. I'm not sure about everywhere, but everywhere else, but at least locally to where it is, you can approximate what the function actually is using a infinite sum. Um, so that's what that third equation means. Um, and so you can always approximate that. And then eventually Euler ended up applying that concept and developing this series for E. Um, and so the main takeaway again is we have something infinite and we can approximate it symbolically and algebraically um, with a few elements. We don't even need to use all of them for most cases. And so this just enabled this again this infinite sum to be easily approximable, and it made it possible to model growth, decay, and oscillations, which will be more obvious later. And again, the last one's Taylor. So now we're going to talk a little bit or start diving into this concept of oscillations. Um, Oscillations are really tied to complex numbers. So you're what I think you cover in pre-calculus, but it's still pretty tied to geometric concepts. Um, so these three, Euler, D'Alembert, and Lagrange were all really important in developing this. So as I mentioned there, Euler unified the exponentials in trigonometry through one really key important observation. Um, D'Alembert was the one that formalized the wave equation, I think it was for strings, like I think it was in the context of music. Um, and Lagrange developed a discrete physical model specifically for springs, I think. I think that was for springs. Um, and so you can see that there's a funny notation there, which I'll talk about. But going into the actual concepts, Euler enabled something really important. Um, so if you look back at this equation 4 here, you have this sum of uh again exponential exponents of x and over some factorial term. If you look at 1, uh it actually really closely resembles 4. Um, and if you add them together, as well as multiplying, I think 1 or by I or something like that, then the exact form that you get is this new equation that Euler pretty much just, I mean, it was probably not hard to notice that they were very related. Um, so this enabled really compact representations. It made it really easy to take an even deeper look into all these complicated results. Um, and that's really important for the rest of signals, as you'll see. Um, then there's the wave equation. So this one it's not really obvious why it's important. Um, it would be more obvious in a functional analysis class. But the main result uh, that you want to take away from that is that you can quantify the dynamics of it, one, but two, there is something tied to somebody later who formally worked more on this and made a really weird observation that led to pretty much the actual like fundamentals of signal processing. Um, and then finally is Lagrange's equation. So you see that there's this notion of discreteness. Uh, it's operating over samples. That X double dot. So back in the day when people didn't know where derivatives or integrals were, they would just say dot for one derivative that was being applied. So the second dot is pretty much the equivalent of acceleration. So there, he's just saying that the acceleration is related to the previous three positions of the spring. Um, so that again introduces this kind of idea that there's a linear model, a discrete model that can represent these dynamics. And that's a really important observation. Yeah.
So instead of three previous positions, one of those that X and plus one third.
Okay, I said three previous. I guess it's only the current and the previous. XM plus one is I I'm guessing that it has to do with the expectation of it. Or at least that's probably the because okay, so what happens is that there's he would collect the data and then do this like make this observation like afterwards. So it was discretizing it over the time series. This is not causal though, but I said three previous, it's not the three previous, it's the future one with respect to the one it's currently at, the current one and the past one. So yeah, that's a good point. And so there's the main takeaway is that you can discretize something that's normally continuous. Um, and so the impact is that Euler, this formula is going to show up again and again and again from now on. This one um is gonna lead to a really important observation by someone, and the last one is again just a discretization method, which is important for our systems because we don't have access to infinitely many things. So discretizing them is really important. And so now we get to pretty much the most important event that happened for signal processing. So they're actually unveiling pretty much spectral content, and I don't think they understood back then what the results meant, and that doesn't matter because we know. But pretty much there's two leading figures at this time that worked on these problems. It was Fourier and Laplace. So Fourier managed to represent signals in terms of sums of sinusoids. That's where this notion of frequency and harmonics, oscillations really plays an important part because all you're doing is, I mean, you're writing it specifically in terms of frequencies. So that's a pretty cool observation that he managed to make. And he was able to do that just to dive into a little bit of the lore. He was interested in the heat equation. I think he got a patent or not a patent, a grant from Napoleon to work on that. So back in the day, I think he was in some important family or something. Napoleon was like, work on the heat equation, and he did. And the heat equation actually has the exact same form as equation two. So U is just some observable thing. T is over time, and X is position in a 1D coordinate system. So he made a really important distinction, which is if you look at this, he wanted the time and position ideas to be independent of each other. So he expressed the heat equation in terms of pretty much two components, and then the rest is uh, the Fourier transform pretty much. Um, and so yeah, the main takeaway from his work is you can write again as an infinite sum pretty much all the frequency content. and there's a Fourier transform to accomplish that. So you pretty much are able uh, to measure this as well. And then Laplace, Laplace takes it a step further and even gets into this idea of um, generalizing it. So there's a possibility for understanding transient behavior. So you don't really need to know what that means, but steady state is just something that we can quantify statistically as oscillating. And then transient usually is the random nature. So like the initial conditions of the system um, until it achieves the steady state behavior. Um, yeah. Fourier essentially just shows that oscillations are building blocks of all signals. Uh, Laplace extended this, and this e to the s thing, st in the third equation, um, became the basis of pretty much all frequency-based analysis on signals. Um, and so this was, again, this was really important because Fourier pretty much lets you see the frequency content of a signal. It allows you to filter things. So if you know that if you have in mind, for example, in audio, speech is from 0 to 5 kilohertz. Um, but audio in general is up to 22 kilohertz. If you only are interested in speech, then your bandwidth should only be limited up to 5 kilohertz. And you can make a filter that specifically does that too. Um, Audio and image compression, that has some interesting ties to like information theory, but we don't really need to get into that. But there's a notion of downsampling and upsampling, and how much information that preserves, that can be observed from this from Fourier's analysis. And then again, Laplace is just a generalization of Fourier's work. So you can get into really complex control analysis. It's most important for filter and circuit design. Um, that's probably where it really shines. I think it's really commonly used for capacitor and or systems that involve capacitors and inductors because they behave so oddly. Um, that's, I guess, stability assessment. I don't really know what this means, but on the left is Fourier and the right is Laplace.
Like a quick question. So like, I know that you have like there are different kernels that you can use to like basically filter out different things from like signals, right? So I was curious, like I think in one of those slides it says that Fourier enables like filtering. So I've never like, I mean, maybe I've like not understood much about that, but I was curious how you basically design a kernel function, like essentially. Like I feel like I know that that's a big part of signal processing. So
Yeah. So that's a good point. Pretty much what happens is that with these Fourier tools, you're able to see what the spectrum looks like. Um, you may not always be able to do that in real time, and we'll talk about doing that in real time later. But if you're not able to do it in real time, like back in the day, they don't have computers. You look at the spectrum that you calculated by hand, and based on what the function is, you have a sense of measurements. So perhaps like you'll know that from 0 up to some frequency, it acts like this. It's significantly decayed in another part, and it's more increased in another part, whatever. So you have a notion of the dynamics. And so then you can design a system based on whatever it is that you want to extract spectrally from that. So the actual filter design, there's a really cool property in the Fourier just frequency domain in general that your filter has a multiplicative effect on the spectral content of a signal. So you can pretty much just design a function that literally attenuates the frequencies that you care about. And then the hard part is undoing that effect. So taking the IFFT, you have to do the inverse Fourier transform. That part is not fun, but luckily there's been enough analysis on that, so most of the time you don't have to do it. But yeah, the the idea is that you can just design these filters. So right now we're looking at the continuous implementation of that. So you don't need to get into as much detail as necessary, but the discretization part is where things really start shining for these methods because that's the only way we can operate on them most of the time. Um, so that's a good question. Did I answer your question?
Yeah.
Okay. Um, okay, so then the next step is to really, face uncertainty, and you do that using your expectation on things. So this is kind of the rise of probability theory in general. Um, Probability is this measurement of what you're expecting to see. So that's where this expectation notion comes from. Thomas Bayes did a lot of the really essential groundwork on this notion. I forget the I read it yesterday that there was like a really interesting phrasing of it at least, but it's like rationalizing your beliefs based on evidence. And you can see that really clearly in the first equation. Um, so you can have some anticipation of something, and with the new evidence, you're able to update your beliefs. Um, and so there's just a really rational framework, and this is used all the time in machine learning and statistics. Um, Laplace was also not as prominent, but he posed a really important question or thought experiment that I like personally and kind of inspires me in the context of this domain, which is this idea of having a daemon that knows the state of everything at all time. Um, so if you as an entity know everything at all time, are you able to know what's going to happen next? Under those assumptions, my answer personally would like to be yes. I would like to know what the next thing is. Um, so I think that it's possible to model all things, and that's kind of why I'm so interested in signal processing. Um, so I think that it's a really important thought experiment, and it bridges determinism and ignorance.
But the thing is you want to be able to predict the current randomness in people's actions from the current state.
Yeah, if you know the current state of the human, I mean, it's a theoretically it's an entity that knows everything, the full context of the human. So I think that it could predict. Um, but yeah, so it's a cool thought experiment, and I think it's fundamental to most of this work. Um, and so the next important guy was Gauss. I mean, this guy is actually something else. Um, he modeled error and deviation pretty much that formula, and I probably expressed it. I should have expressed it better. I should have used like G, and it's normally G or N. The normal distribution is the other name, but that's the most meta expression for that. And there it ties into a bunch of stuff, specifically in statistical signal processing and machine learning. A lot of the results tend to show that noise is usually Gaussian distributed, which is a really odd result, but pretty cool. Um, and so ultimately, again, on the left is Bayes, on the right is Laplace, or sorry, Gauss. I already showed Laplace. I'm not going to show him again. Um, and so Bayesian inference is pretty much really important in this notion of discretization. Um, if you know the previous thing and you observe this new thing, what kind of update should I make? So it's important for adaptive filters and probabilistic estimators. There's also, Laplace's worldview, which I already talked a lot about, and Gaussian noise is just the basis for a bunch of estimation and filtering, which we'll see is pretty important in with Norbert Wiener. So now we're getting pretty close to the modern. most of this work was done in the 1950s, I want to say, 40s, 50s. So uh, Kolmogorov was this probabilistic mathematician, and actually we have one of his students attends UF, um, Shabanov. So he's a pretty cool guy, and he was able to formalize a lot of the modern probability axioms that we use now. Um, and Norbert Wiener was just this cracked cracked guy from MIT who formalized a lot of the work on stochastic processes and filtering. Um, Kolmogorov's axioms pretty much just defined probability as a measure. I'm not even going to get into what sigma algebra is. You guys don't care, but um, it's just a really rigorous treatment of completely random processes. Um, and usually, just to give an idea, is this notion of your input space, your event space, and I think it's the probability field or something like that. Um, Maybe I'm confusing the name for the probability field, but I know that there's input space and event space, and you're just essentially doing a bunch of mapping work with that. And he really formalized that. It's really interesting. Um, then there's the next important thing is this stationary process. So the stationarity assumption is horrible all the time. It never works, but the truth is that over small segments of time, things tend to be stationary. So you can always upsample things, and then there's a period of your sampling time, over which things are stationary. So you can take advantage of that. And it's actually really critical in signals. Most of the fundamental assumptions are that your signal is stationary, even in adaptive filtering. Your assumption is that it's stationary, but that you're able to then there's I'll get into that, but there's a way to adapt these really quickly. Um, and so the next important thing was the Wiener process. I mean, the Wiener process was actually shown to us really recently by Shabanov, so I wish he could redraw all of that because I almost all of it went through like over my head. But it's this crazy idea that um, you just have this signal that is nowhere continuous, but can but has measurable quantities to it, pretty much. Um, so there's this notion of something like mean, something like uh, variance. So it's just really, really random, but you can still estimate a lot of really important measures over it. Um, so the important thing with the Wiener process is that uh, it's pretty much now being studied. The stochastic processes, you can measure things that normally would not be measurable. Um, Finally, there's the Wiener filter. So again, this guy working on, I think it was in World War II, working on or no, a little bit after, um, working on an automatic. The first works on automatically locking onto airplanes, uh, like to shoot them down. It's pretty interesting, but it's the fundamental idea of controls. Um, so you use Wiener filters. They're pretty much optimal under the assumption of a Gaussian noise, and they estimate pretty much the signal, the dominant signal statistics optimally. So you can see at the top actually, um, the first one is this notion of stationarity. So the expected value of x. Um, you guys know like the integral formulation for it? So pretty much it's constant. And so your autocorrelation is only a function of the time difference. And if your estimated value is constant, then usually it's going to tend to be decaying to some degree. Um, Again, the Wiener process is this notion that you just have this completely random signal, but you can model how it behaves based on a mean and a variance, and that pretty much fully captures most of the important dynamics of it. And then the Wiener filter, uh, all it uses really is this criterion over the optimal, theoretically the optimal estimate and what you have, and it minimizes the expected value of the output. So it's pretty much just um, linear algebra on crack, and you have to use really big matrices for it. But it optimally predicts it, or it optimally generates the filter weights that would be desirable in this case. So again, going over the insights, Komarov founded probability theory. Most of that I mean, it is fundamental to pretty much everything we do at this point. And Wiener made this tool set that or he founded this like randomness idea that still has usable quantities, as well as the actual filter itself, an optimal filter and that can optimally predict based on that assumption of Gaussian noise. Um, and so you can model real world signals, you can filter, predict, and you can do a bunch of really cool things like controlling outputs or learning how to control outputs, as well as statistically learning important things from your data. And I think this is the final slide, but this is pretty much the most recent that I'm going to go, although there's some pretty cool stuff happening now. It's just machine learning as a field has saturated, or is saturating because of the nature of most of the research. Woodrow was the guy that made least mean square algorithm. So it's pretty much an extension of Wiener's equation. I forget, is there a name for it? No, there isn't. But it's just pretty much there's an understanding that it's a biased estimator of the Wiener filter equation, the optimal Wiener filter equation. And so you can pretty much approximate whatever the Wiener filter should be using this uh, stochastic thing. And so that was really important, especially for adaptive filters, because if you have something that is changing, ideally you'd want to be able to capture those dynamics and adapt to them. So, for example, my hand might not always be moving, but then I start moving it and you want to be able to capture that. And then maybe I could stop and keep going. You want to be able to adapt to that. So that's in the context of like computer vision or something. Then there's the common filter, which is more of a probabilistic model of these kinds of things, but it still holds the same idea. You have an estimator based on the previous state, and you really just want to create an update that best predicts the next step. So we're not gonna. It's recursive again. So if you guys know the idea of IIR filters, it's kind of similar to that, but it just uses the last state, which is kind of like the first equation too. So you can see it's actually really similar. And then Vapnik is another goat. I actually thought he was dead, but he's not. He's just in Colombia, um, just chilling right now. And he wanted to he he was developing the theory of learning, and its robustness, um, the robustness of models in general. So he did a lot of statistical work in quantifying that, mathematically. So you can see that I don't even know what that means. It's just that when I searched it up, that was associated with him. But I'm pretty sure the actual notion is something like is the loss with respect to whatever your model does on the sample, the prediction, the true prediction, sorry, and then it also adds, I think, a scalar times the model complexity of the function that you're applying to it. Um, and it says that your your model will only have as much risk as the minimum of whatever element minimizes that. Um, so it just says, more complex models can overfit, and complexity is a really big proponent in optimal predictors. Um, And so, I mean, all of these ideas are really prevalent in time series. I mean, the common filter is probably the most used filter at the moment for adaptive systems, especially in the context of defense and like say air guided missiles or
So I was curious, like by filter, do you just mean like a function that extracts like some meaning from like a signal?
yeah. So I mean, okay, so maybe I can clarify that. Filter is like a pretty much a weighting function. So it's like in neural, it's basically a one layer neural network.
Mhm.
Um, so you can have these actually it's a one node neural network is what a filter is.
Mhm.
Um, so you have like all these individual samples, you could say through time. It weighs them and then it outputs something based on that.
Mhm.
Um, that's pretty
Oh,
much what a
I
filter
see.
is.
So like potentially like if I have like four different signals coming in,
Mhm.
it's just like weighs them on the output signal.
Mhm. Yeah, so I mean, I mean, I know there's a lot of research done into multimodal uh, signal stuff as well. Usually for time series, you look at like past samples, because having a bigger context tends to help. If you're working in something like adaptive time series, then that context actually really matters, because you want it to be able to adapt or quicker, so you don't want it to be too long. But those are all very technical details. Um, yeah. So you can use a bunch of samples. Usually you want a decent amount of context. So you would feed in a few, maybe like a vector of uh you treat one signal as a vector um over some history. Um and you can use, I mean, images, you can use whatever you want. CNNs are deep learning pretty much builds on all of this.
Mhm.
So it's pretty analogous. Um so why is all of this important? Again, it's the foundation of adaptive filters, state-space modeling, machine learning. You can use it for all kinds of signals, analyzing EEG data, which I'm doing right now, radar, so communications. You can analyze a bunch of like, I forget the word. What's like that earthquake data? Like how like the earth is moving, whatever that is.
Size of data.
Yeah, probably seismic. Like I think that's how they first did that like analysis. If you wanted to find fossils or fossil fuel what's that shit called? Whatever ExxonMobil is, they love signal processing engineers because they need to find gasoline in the earth. Um, so that's like a really random but applicable thing. Robotics, I mean, I think that's pretty clear why. Speech again, finance, stocks, and more. Um, stocks is a little harder because there's like some weird context stuff going on. And vision too. But yeah, all of it is weird because there's a bunch of notion of non-stationarity. That non-stationary problem is a tough one. But pretty much this, I mean, this shows that signals, aren't just processed. You can learn a system that is able to operate on them. And so on the left is Woodrow, middle guy is Common. I think he's already gone. And the last one is Vapnik. And that guy's in Colombia right now, I think. Um, and so today, we're wondering about artificial intelligence. Is it possible and through what means? Um, we've pretty much traced everything from Newton's motion, to Fourier, Common, Woodrow, Vapnik. We want to know if models are able to fully capture these signals that we're interpreting all the time. I mean, as humans, we're signal processing machines. So we ideally we would like to make machines actually do that as well. Um, the main thing that we need to look into is that signals don't really signals aren't something that we can only observe at this point. We can also look into the actual details of a signal. So we can make predictions and adapt decisions. And so AI currently the meta of it is to, and actually something that I want to talk about is the meta is to kind of have like this, with LLMs at least, a memorization system or box that just memorizes common, really important, it memorizes whatever is fed into it. And so there's no adaptability notion to it really. And improving on that is probably whatever the next step is going to be, which I think is what Titans is. But um, I think that's it. Any questions? You can just ask life advice. Okay.
I have like one question about like cardinals. So like one like I don't have like much signal processing background. So like the first time I saw cardinals appear was that in biological neural networks, you can potentially model them by assigning a kernel function to like each neuron. And essentially what they do is that they put an input signal through the neuron and then they like convolve the kernel with the input signal and then check, if the convolution goes above a certain threshold, then they say it's spiked, otherwise it
Spiking
doesn't
neural
spike.
networks.
So like the question I had was that like with specifically for like kernel designs that like how would you pick out a kernel that can ideally like filter certain things out? That's like if that sort of makes sense. Like how do you pick one kernel out over another one?
In the context of
In the words of like anything, like say you're given like a certain problem and you're supposed to like design a kernel to like do something. I'm guessing for like something like image processing, it's sort of intuitive because like you can, I don't know, maybe align the diagonals of like a kernel to like check for diagonals.
Yeah.
But when you have like let's say a continuous kernel function, how do you go about doing something like that?
Continuous kernel functions, there is continuous kernel function approximators, and that's kind of, I mean, I call them, in my mind, that I keep on thinking of them as a support vector machines, which is this notion of creating a space where pretty much you map some vector input space, so Rn, you map it to a smaller dimensional space, so let's just say R, and you pretty much approximate like a function over it. So those are the kernel methods that I'm currently like working on with Principe, and it's the thing with them is that they're really sparse, but it's possible to approximate nonlinear functions with them. So
Well, like still like I guess like that you mentioned support vector machines like something that comes to mind is that you have like these kernel functions that you can pick and choose from. And like in the concept of like SVMs, some of them might work. So like somewhere a polynomial kernel might work, somewhere a like sigmoid kernel might work. Given like let's say a certain problem, like this is something that I've like tried to read up on and just could not figure out. Like, is it like a trial and error game, or like how do you like pick out the optimal kernel? Like, there's so many different ways to design your kernel essentially.
For spiking neural networks, those are difficult because currently neural technology is not fast enough most of the time. Um, you you need like a crazy sampling rate because most of at the very least like EEG operates up to like I want to say 130 hertz. So ideally to have like full resolution of what um you need like I think it was like 10 kilohertz or something, which is crazy, but you need like 10 kilohertz, and that's only available through imaging techniques currently.
I guess like potentially like maybe like I get what you mean by like, the hardness of designing call functions for like spiking neural networks, and that makes sense. But maybe like let's say if we go for like SVMs, imagine we have like a really high dimensional problem that we're trying to solve using SVM. Like how would you like just like go like you need like some kernel function to like basically like solve your like SVM, right? You need to find like the kernel the kernel values between like every like data point in your like thing. So how would you like go about actually finding such a kernel function that works? That's not.
When you're talking about kernels, are you
I'm not sure
like the filter
defining
itself or
no
the
not the
function that you
filter like
apply
the
to?
function like the inner product space that you define.
Okay.
Yeah,
Yeah, so the usually okay, so you
I guess that's a different question.
yeah. No, but it's a good question because I'm still learning about it too a little bit. But as far as I understand, you want universal approximators. Um, so universal approximators in this space are usually going to be things with limited bandwidth. So kernels like for example, like the Gaussian. The Gaussian has a pretty limited bandwidth. You know like three sigmas away, and you're already 99% of the area, right? So its bandwidth is pretty contained. So what that means is that you're able to do this mapping to a higher dimensional to a different space where your representation of the input space is pretty sparse. So all you would need to fill that in is more data. So then there's a trade-off. There's a trade-off between the kernel bandwidth itself, and the number of data points you want to use. So if you have a lot of data, then you can make the kernels more sparse. But if you don't, then you want to make them really big. And there's a lot of actually one of the works that helped me understand that was with Dr. Principe, QKLMS, if you want to look into it. KLMS is like the fundamental algorithm that helps you understand it. But QKLMS taught me the importance of like sigma, because it's a quantized version of that. So pretty much what they do is that they have like they make these cells that have like like gigantic bandwidths. And you use this thing called surprise, which is it pretty much rates the statistical importance of this new sample, and it'll add it to the model if it's important, and if it's not, then it'll just update the current weights. So the main takeaway from what we were talking about is the sigma, the bandwidth is going to be the main thing. If you don't have a lot of data, and in general, more data is more good, but if you don't have enough, then you have to make a bigger bandwidth.
Makes sense, yeah.
But in general, all these kernels are going to have a notion of like bandwidth used to them. I think in spiking, that stays like exponential decaying functions, right? So you just make it a little smaller. You do have to tune it. You have to play with it a lot, which is the annoying part. I haven't even in my experiments we haven't even gotten the chance to actually work with the data. But like we were talking about it, and they're like, oh, we're sampling at 1 kilohertz, and they're like, you're not even going to be able to make out what's going on. So we have to somehow like interpolate the data. We're trying to do blind deconvolution to recover it up to 10 kilohertz. Basically like interpolate the data artificially. It's odd, but it's pretty cool. Um, any questions? Okay, yeah.
How did you generate a picture of the young man who's in start? What's the inspiration behind that?
This guy. I went to chatgpt.com and I went to ufdsi.com and then I right clicked the image of oh no, actually I went to aiiri.com.
Yeah.
I went to the thing that said Mateusz Kunzler Maldener Hall of Famer. I clicked on the post, I right clicked on the image that was of him, and then I posted it into ChatGPT, and then I said, make him broke as fuck, and this will shut up. Yeah. Yeah, images are signals. And that's how I forgot. I think somebody made a post about how they actually do it. It was pretty cool. Um,
Is the spotlight going down the scene?
yes, that too. That too is a signal. Okay. Yay. Um,